Hi and welcome to another lesson about Bitwise operations. This time we are going to speak about Bitwise instructions. Objectives of the lesson. We will learn about the logical instructions NOT, AND, OR, and XOR. We will learn about some instructions that move bits around, which is about simple bit shifting with respect to the sign, and finally, rotating bits. Logical instructions. So far we have considered the bits inside our registers to have numerical meaning, which means that we looked inside our registers at their content and thought about them as unsigned or signed numbers. Actually, we always thought about them as numbers. We didn't give them any other meaning. However, we could think about other meanings to bits. As, for example, we've seen in the Boolean algebra chapter, we can think about true as the bit 1 and false as the bit 0. And these are the Boolean values. We would like to be able to perform meaningful operations between values of true and false, or maybe between ones and zeros, just like we learned in the Boolean algebra chapter. Let's begin with the NOT instruction. It has the following signature: NOT and dest, which is just one argument. The NOT instruction actually flips every bit inside its argument, which means that it changes 1 into 0 and 0 into 1 for every bit inside the argument dest. I remind you that NOT is an unary operation. It works on 1 bit every time. Let's look at some examples. NOT EAX or NOT CH. These are two different examples. In the first one, 32 bits are going to be flipped. However, in the second one, only 8 bits are going to be flipped. Let's take a look at a more specific example. Let's take this example, NOT CH, and try to invoke it on real numbers. First, we move this binary number inside CH, and then we invoke NOT. Let's see what happens. This is the original number that we put inside CH, and this is the result. We can see that every bit is flipped. 1 turns into 0, and 0 turns into 1. I want to remind you that this instruction, the NOT instruction, is not the same as the neg instruction. The neg instruction is like doing NOT and then immediately adding 1. Neg instruction is an arithmetic instruction. It really understands numbers. However, the NOT instruction doesn't give the argument a meaning of a number. It only treats the argument as a set of bits, a set of consecutive bits. AND. The AND instruction takes two arguments, dest and source. As we already know, this is a binary operation, which means that it produces 1 bit from every 2 bits. It produces 1 if the first argument is 1, the first bit argument is 1, and the second bit argument is 1, and it produces 0 otherwise. This is the truth table of AND, in case you don't remember. Let's look at a concrete example. We move those two numbers, this one and this one, inside the registers AL and DH. For this example and also the NOT example, I chose registers of size 8 just to make the example easier to understand. I want to make sure that you understand that AND, NOT, and also all the other instructions that we are going to see work on every size of argument. They can work on arguments of size 8 bits, 16 bits, and 32 bits, and so on. So here we AND those two registers, AL and DH. And we get this result. Let's try to see what happens specifically. This is the value of AL, the top row. This is the value of DH, the bottom row. For every 2 bits, we AND those 2 bits. So 1 and 1 equals 1. 1 and 1 equals 1. 1 and 0 equals 0. And for example here at the end, 0 and 0 equals 0. So this is pretty simple. We just AND every 2 bits. We AND bitwise. The OR instruction. The OR instruction, just like the AND instruction, takes 2 different arguments, dest and source. OR is also a binary operation. The OR instruction works bitwise. It checks every 2 parallel bits in dest and source and produces an output, which is stored back into dest. It produces 1 if the first bit argument is 1 or the second bit argument is 1, and it produces 0 otherwise. Let's look at an example. We put this number inside AL and this number inside DH. Those are actually the same numbers from the previous example. We just use a different instruction here. And then we OR AL and DH. So we have AL in the upper row and DH in the bottom row. And now we OR every 2 bits according to this truth table of OR. So we get 1 or 1 equals 1. And maybe here 1 or 0 equals 1. And here, for example, 0 or 1 equals 1. And here we have 0 or 0 equals 0. XOR. The XOR instruction takes 2 arguments, dest and source. It is a binary operation, which means that it goes bitwise over every bit in dest and source, the parallel bits, and then it performs XOR over those 2 bits, 1 bit from dest and 1 from source. It produces 1 if the first bit argument is 1 or the second bit argument is 1, but not both of them at the same time, which turns it into exclusive OR. This is the truth table of XOR, as we have already mentioned. Let's look at an example. We have here the same numbers, just like in the previous examples, but this time we use XOR. So here we have AL, and this is the value of DH, and we XOR bitwise. 1 XOR 1 equals 0. 1 XOR 0 equals 1. 0 XOR 1 equals 1. And another example for a pair, 0 XOR 0 equals 0. So eventually we get this result. Zeroing using XOR. The following piece of code is very common. In fact, you are going to see it in almost every piece of assembly code which is large enough. Whenever an assembly programmer wants to zero a value, it will usually use this expression, XOR EAX, EAX, or maybe XOR EDX, EDX. This expression is used because XOR EAX EAX has shorter encoding than move EAX 0. Let's look at the specific encoding. This instruction XOR EAX has this very short encoding, 31C0. However, the instruction move EAX 0 has this large encoding. Note that you could actually put two XOR instructions and still have one extra byte, which means that the XOR instruction is much shorter than the move instruction when stored in memory. I remind you that when you XOR two values which are equal, you always get 0. You can easily see this from this truth table of XOR. When looking at the main diagonal, we can see that everything in the main diagonal equals 0. That means that the XOR of two equal values equals 0. Bit shifting. So far we could only invoke Boolean operators on parallel bits. And what do I mean by that? For example, we could take the two bits, bit number 3 of EAX, together with bit number 3 of EDX, and then we could maybe OR them or XOR both of those bits. However, what if we want to end bit 3 of EAX and bit 5 of EDX? We can't do this using the previous instructions that we have learned. We can only end bit 3 of EAX with bit 3 of EDX, or maybe end bit 5 of EAX and bit 5 of EDX. But we still can't combine bit 3 and bit 5. We would like to have finer control over individual bits. So now we are going to learn how to move bits around. So we can actually combine bits and do operations on different bits in different locations. We begin with shift left and shift right. Those two instructions are really dual, they just move in different directions. The shift left instruction has two arguments, dest and another argument which I call k. It is sometimes called source, but I prefer k for this example. This instruction shifts the bits inside dest k bits to the left, and it inserts zeros from the right. The dual instruction shift right also has two arguments, dest and k. It shifts the bits inside dest k bits to the right, and it inserts zeros from the left. Let's look at an example of the shift left instruction. First we put this number inside AL, and then we shift left AL by 1. We have this picture on the right which describes what happens before and after the instruction. This is what happens during the instruction. This is what we have inside AL, which is just like this number. Every bit is shifted one slot. For example, this bit, this one bit, is going to move to the next slot, and this bit is going to move to the next slot. You might be wondering what happens with this slot, what will be inside of it. A 0 is inserted into this slot, the rightmost slot. The last bit that gets out from AL is not gone. It is moved inside the carry bit. So as a result we get this picture. The carry bit now contains this bit, bit number 0, it moved here, and every bit is shifted one location to the left. For example, this bit 1 moves here, and this bit 0 moves here, and so on, until the new 0 is inserted to the rightmost location, to the rightmost slot. So we get as a result this value, AL equals 100, 10110, and the carry flag equals 0. Some other things to know about shift left and shift right. The boundaries. The carry flag will contain the last bit that was kicked out of the boundary. It could be from the left or from the right, it doesn't matter. Both of the instructions, shift left and shift right, store bits inside the carry flag. Shift left kicks out bits from the left, and shift right kicks out bits from the right, and those bits are inserted into the carry flag. The carry flag will always contain the last bit that was kicked out. And I say the last bit because maybe we want to shift left more than one location. Maybe we want to shift left 3 locations. Then the carry flag will contain the last bit that was kicked out. The new inserted bits, and it could be from the right or from the left, depends on which one you chose, shift left or shift right. The new inserted bit will always be 0 in those 2 instructions. Some constraints over those instructions. The K argument, which chooses the number of slots to shift, can only be one of the following. It could be a small number, and by small number I mean no more than 1 byte. It could be from 0 to FF. It could also be the CL register. It can't be anything else beside a small number and the CL register. So for example, this instruction, shift right EAX DH, will not assemble. The assembler will give you this error, invalid operand, because you cannot put DH here. You can only put a small number or the CL register. This instruction, as opposed to the previous one, will assemble because you chose CL, and CL is an okay choice. It's okay to choose CL. Let's look at a more concrete example of using those instructions. We begin with DL equals this number, and then we move 1 into CL. First we shift right DL by CL, which means shift right by 1. And so we get as a result this number. We also get that the carry flag contains 0, because the rightmost bit is 0. Next we move on to shift right DL2. We just take the previous result, which is this, and shift it right by 2 locations, and we get this result. We can see that zeros are inserted from the left. We get that the carry flag equals 1. Why is that? Because this bit, this 1 bit, was the last one to be kicked out of DL into the carry flag. Finally, we shift left by 3. And we get this number. In this example, you can see that we shifted right first by 1, then by 2, and finally we shifted left by 3 locations. So basically, we got to the same location in which we were in the beginning. However, we overridden some bits with zeros. You can see that this value, the final value of DL, looks pretty much the same as this one, except that we overridden those 3 bits with zeros. So this 1 bit was cleared.